Okay, and people have done this endlessly with all kinds of experimental and observational data. And I should get the same answer regardless of what t is, yeah? Because as t goes up, right, this changes, but also this changes, and I should get the same. If your preferences are accurately described by the discounted utility model, it shouldn't matter how far out I make the delayed payoff. So suppose, for example, for t equals 1 tomorrow or next week, or well, sorry, in this case it would be next month, I say how much would you need in a month to make you give up 250 now, and suppose you say 300, then that says 250 to you is delta times 300, and that implies that delta is equal to 250 over 300, which is approximately equal to 0.83. Okay? What does that imply for x12 a year from now and x120 10 years from now? Again, maintaining the assumption that your preferences are accurately described by the discounted utility model. Okay, so x12 is going to be equal to 200. Sorry, let me actually write this out because it'll be helpful. x12 satisfies this. 250 is equal to delta to the 12th times x12, which implies that I can figure out x12 if I know delta. It's just equal to 250 over delta to the 12. And if I plug in 0.83 for delta, I get approximately $2,339. You might think that that's a kind of large number, but maybe you needed that 250 right away badly. However, if we then say what would you be willing to, how much would you have to be given in 10 years, what we get is that x120 is equal to 250 over 0.83 raised to the power of 120. And that number is 1.284 quadrillion. I don't know about you, I would accept less. Anytime your answer is measured in gajillions, you should be suspicious. Dick Thaler in 1981 in a paper that's on the website. Is everybody pencils down at this stage? Okay. Thaler went and actually asked people this. Now, this is all hypothetical. He didn't actually give anybody the 250 or the 1.284 quadrillion. And he asked, basically, he did this for a lot of different numbers, but one of them was $250 now or in 6, 12, 60 months to make you indifferent to 250 now. Wait a minute. I thought I had, no, sorry, this is a mistake. That 6 should be a 1. I apologize. So 1 year, 1 month, 1 year, and that 60 should be 120. I apologize. Yeah, 1 month, 1 year, 10 years. And this is what he got, okay? So that's x1, that's x12, and that is x120. You could claim that 400 is not that different from 2,500, but you don't get to claim plausibly that 1,000 is not different from a gajillion. Then, if he takes these numbers seriously and uses them to compute the delta that they imply under discounted utility, what he finds is that when it's a month out, the implied delta is pretty small, but when it gets out into 1 year, 10 years out, the implied delta starts to get pretty close to 1. Okay, so the time horizon over which you estimate delta affects strongly what your estimate of delta is going to be. Okay? Subjects appear to be more patient in the long run than in the short run. They're willing to wait for a smaller payoff in the long run than the model would imply. You can see this in the paper. This is basically looking at the imputed discount factor delta. Whoops. That was determined in a whole host of different studies. You can look at what those different studies actually measure. And then this is the time horizon that they use. And what you basically find is that for horizons under about a year, you get these very small numbers. And then once you're above a year, everything is in a sort of fairly similar band. And what that suggests, again, is that people seem to demand very, very high proportional rewards to wait a short period of time compared to how much they need to be paid to wait a long time. Okay. So that's the first implication of this discount function. Now, it's also the case, and this is closely related, if delta is constant over time, right, if how you discount any two periods is the same over time, then you should feel the same, for example, about a 2-week delay now as you feel about suffering the same 2-week delay in a year. Right? So if I ask you, would you like $100 now versus $105 in 2 weeks, your answer should be qualitatively the same as, would you prefer $100 in 52 weeks or $105 in 54 weeks? And let me demonstrate that to you. It's actually mathematically extremely straightforward. So if we define t in terms of 2-week periods, okay, so delta is a 2-week discount factor. And now let me not make any assumptions about the instantaneous utility function. If you prefer $100 now to $105 in 2 weeks, which I think a lot of you said that you did on the first day of class, what I can say under du is that that means that your utility from getting $100 now is greater than your discounted utility of getting $105 in 1 period from now, right? So discounted by delta, okay? Which in turn implies that your delta is less than the ratio of these two utilities, okay? So if that's the case, then what can I conclude about your choice between $100 in 52 weeks and $105 in 54 weeks if discounted utility, the exponential utility model, or exponential discounting is the right model? Well, I should be able to just multiply both sides by delta to the 26th, right? I mean, if this is the right model, then that's the right math, and if that's the right math, I should be able to manipulate it according to the rules of math. So if I do that, what I get is that delta to the 26th times the utility of 100 should be greater than delta to the 27th times the utility of 105, okay? But that exactly tells me that you prefer 100 in 26 weeks to 105 in 52 weeks, because the period is 2 weeks, to 105 in 54. Right? And if in fact I find the opposite, which I think many of you said was the case for you, that in fact if I push this delay out a year, your preference would be reversed, that you'd rather wait an extra 2 weeks for another $5, then what that would suggest, so actual prefs imply that your delta is actually greater than u of 100 over u of 105. So, sorry, that shouldn't be a d, that should be a delta. Okay, so I've got one set of preferences that implies a small delta, another set that implies a large delta. Something must be wrong. Right? Now, it could just be some error, but we find this very consistently with lots and lots of different people. And if it happens to not be true for you with 100 versus 105, I can pick numbers that make it true, I promise you. Okay? So something must be wrong. We're out of time-wise. I'm going to skip this slide. No, I'm not. I'll tell you what I'm going to do. I'm going to write down the first line of math, and then you can do the rest. So if you're choosing at period 0, you're choosing what to do starting in period 1, choosing between plan A or B, and outcomes for these two plans don't start until the next period, right? So you're making a choice now about something that's going to have impact in the future. Under du, if you choose plan A at time 0, it means that u0 plus delta, okay, I'm making a simplification. Instead of writing u of x0, I'm just writing u0, plus delta u1 plus delta squared u2 plus dot 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 is greater than u0a, u1a, u2a is greater than u0b plus delta u1b dot 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 dot. And what you can do here is subtract, and since we're assuming that these two plans don't kick in until period 1, u0 is the same for either plan, right? So I should be able to just lop off the part that's the same in both plans, and then divide by delta on both sides mathematically. And what I'm going to wind up with is that u1a plus delta squared, delta not squared, u2a plus dot 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 should still be preferred to u1b plus delta u2b plus dot dot dot, right? So that basically the first period, where the utilities are the same, I ought to be able to just cut that off, roll you forward one period to period 1, and how you feel about these two plans should stay the same. Okay, that's exactly what I did with the 105 versus 100. I asked you when it's a year out. So there's no difference. The plan take 152 weeks and the plan take 105 and 54 weeks. They're identical in the first 51 weeks, right? So I should be able to lop off those 51 weeks, roll you forward to week 52, and ask you the question again, and you should give the same answer. But that's $100 now versus 105 next week, and your answers change. Okay, so under du, that kind of reversal, when I roll you forward, shouldn't happen. And we see it all the time. So many of you confessed that you would reverse your preferences, and there are just countless other examples. You don't even need to test this. We know. Today I want to quit smoking. Next week I prefer not to quit. Today I want to spend this weekend preparing my lectures. When the weekend arrives, who knows what I wind up doing. Okay? So these kinds of preference reversals are absolutely ubiquitous, and they have huge implications economically. What's really interesting, and the paper talks about this. Does the paper talk about this? I'm not sure. There's another paper that I put on the website that's not required that does, by Strauss back in 1955, who demonstrated that if we assume that people's preferences over plans are some kind of weighted sum of their instantaneous utility over those plans, with some kind of discount factor weighting them, it turns out that the exponential discount function that Samuelson adopted is the only discount factor that doesn't generate preference reversals like this. Okay? Now, the set of possible discount factors is an infinite set. And there's only one element in that set that gets you this nice, consistent, time-consistent, rational result. Well, if we just landed from Mars and didn't know what that discount function should be, and assumed that there was some distribution of probability over what function it might be, if there's only one element in an infinite set that actually gives you a result, what's the probability of that one element actually being the correct one? 0. Right? In an infinite distribution, the probability of any one number actually showing up is 0, which is a kind of an odd thing in probability theory. The point is that this is what we call a knife edge case. You get the rational result only if the real answer of what that discount function should be is on a knife edge. Right? How wide is the edge of a well-sharpened knife? It isn't wide at all. It has 0 width. Okay? Now, in standard economics, it is standard practice to always reject models that give you the right answer only on a knife edge case. It's just standard practice. Oh, you know what? Your model crucially depends upon this number being exactly 0 or exactly 1.358 or this functional form being exactly linear. And if it's even slightly off, your model collapses. We just reject that out of hand. Okay? Why not this? And partly it's because we like nice math, but partly it's because we really, really, really like rational outcomes. Because we really, 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 public policy is hard work, and laissez-faire is not. So if your model predicts that laissez-faire is social welfare maximizing, you've just saved the government a lot of money. Okay, we know this is wrong. So we're gonna crank up a behavioral model, which is called a model of quasi-hyperbolic discounting. Okay, so if this is an exponential discounting function, a quasi-hyperbolic one drops off a lot faster. And a quasi-hyperbolic one is something that actually drops off and then does that. And you don't need to worry about those shapes at all. We call it quasi-hyperbolic. Sometimes people just call it hyperbolic. More correctly, it's quasi-hyperbolic. But what we're actually going to call it most of the time is just beta delta, because we're going to add a parameter. Okay? So let's figure out what that parameter should be. So key psychological finding based on what we've seen is what we call present bias preferences. Okay? The evidence on discount factors suggests that we discount heavily between now and the near future, but much less heavily between the near future and the distant future. And the evidence on time inconsistency suggests that we're happy to wait a little longer when the delay is in the future, but we have a hard time waiting when the delay is right now. Both of those things suggest that we have a taste for immediate gratification, or that our preferences are biased towards the present moment. Okay? So how are we going to put that into a model? We're going to do this. This is a favorite of behavioral economists, because what behavioral economists really like to do. So behavioral economists have two big goals. One is to improve upon standard economics, and two is to still be economists at the end of the day and not to get kicked out of the tent. Okay? If you tweak the standard model too much, they'll send you away, and you'll wind up someplace like a business school or a public policy school, and people will stop calling you an economist. And even if you get a Nobel Prize like Oliver Williamson, they'll still sort of say, yes, but that's kind of weird, because Oliver Williamson just abandoned mathematical modeling and went and figured out something that was actually true, which is called transaction cost economics. And for his pains, he was basically ostracized by mainstream economists and had to go and get a job in business school. Nonetheless, you'll see his photograph on the wall of room 6087 Evans, but only because he won a Nobel Prize. Okay, so we really like the fact that we get to keep all of Samuelson's model and just add this one tiny little parameter. We really love that, because that means we get to improve upon the model dramatically and not get kicked out of the tent. Okay? So instead of having a exponential function of time, we're going to say the discount factor is this quasi-hyperbolic function, and the function is this. It's going to be, if t is 0, that's the present, then it's just going to be delta to the t, which is 1. And if t is anything greater than 0, anything in the future whatsoever, it's going to be delta to the t times this beta, this additional discount parameter, where delta, once again, is going to be strictly between 0 and 1. Actually, I should make that a square bracket, because in short horizons and for simplicity, we're also going to let delta be 1. And then beta is some number between 0 and 1, right? Where if beta is actually 1, then this just becomes the exponential discounting model again. Okay? But if beta is less than 1, what this says is that you are discounting everything in the future relative to the present. Okay? So the discounted utility of a plan becomes this thing. So you don't discount, as before, you don't discount the present, then you discount everything in the future by beta, and then you additionally discount things further into the future in this exponential way of the standard model. So what that looks like is u of x0 plus beta delta u of x1 plus beta delta squared u of x2, etc. Okay? That's the model. Now, the way I would encourage you to think about this initially, so you can really see mathematically how this is embedding a preference for immediate gratification or bias towards the present, is to say, in other words, the present period, t equals 0, is inflated relative to other periods by 1 over beta, which is a number greater than 1. Right? So you can either deflate everything in the future or you can inflate everything in the present. Mathematically, it turns out to be more charming to put a beta less than 1 on everything in the future than to put some number 1 over beta greater than 1 on just the present. It's going to make things much, much easier to deal with. But that's conceptually, psychologically, that's what that's doing. Is it's saying we're going to do all of this discounting by exponential discounting by delta, and then on top of that, we're just going to say, yes, but could I just have it now? Okay? And everything else about du remains the same. But we'll find that we can do an enormous amount of work with just this. So I say I've got 3 more minutes. Does that sound right? I lost my watch. This clock says I've got 3 more minutes. I'm going to use them, and I'll try not to. I'm going to get through one of the next 2 slides. So look what happens when we go back to this question of implied discount factors and how they depend upon the time delay. Okay, when we incorporate this beta. Now, if I say, would you like 250 now or xt at some point in the future, t periods out, your answer implies the following. If your answer is xt, it implies that for you, 250 is equal to, and once again, I'm assuming that the u of x is equal to x. Instead of being delta to the t, it's beta times delta to the t times xt, okay? Which implies that beta is equal to 250 over delta to the t times xt. Now, let me take your 10-year answer from earlier seriously, which was 0.99. Let me say, okay, if we get this all the way out to there, we're probably pretty close. So let me let delta be equal to 0.99, and let's suppose that I then go back and say, what does that tell me about beta based on your t equal 1 answer, which was 300? What that implies is that beta is equal to 250 over 0.99 times 300, which is approximately equal to 0.84. Okay, so this is someone who's fairly patient. Delta equals 0.99, but they've got this present bias parameter 0.84, which is actually pretty close to what has been estimated in a lot of data. If that's the case, what does that tell me about what your xt should be for longer delays? Okay, if you say that x12 is a certain thing, I write out 250 equals beta delta to the t xt again, and now I can back out what xt should be. It's just 250 over beta times delta to the t. So if I ask you what your xt should be a year from now, what I get is x12 equal to 250 over 0.84 times 0.99 to the 12th, and that's approximately equal to $355. That's not looking too bad. And if I ask you for your 10-year indifference, x120, I get 250 over 0.84 times 0.99 to the 120th, which is approximately equal to $994. Not bad. Not bad. And I didn't even select those numbers from the Thaler experiment with this in mind. This happens to work pretty well. This model actually works pretty darn well, as we will see over and over again. So next time, I'll walk through the same math that shows you how this model can very conveniently capture time inconsistency, and then we'll roll from there.